So in this section, we're going to define determinants of a matrix in general setting. So suppose that A is n by n square matrix, then the determinant of A is given by this large alternating sum, where A sub ij's are submatrix of A obtained by eliminating the ith row and j's column. So I think the definition becomes easier when you think about an example. So for example, suppose that A is given by, say, 3 by 3 matrix, A, B, C, D, E, F, and G, H, I. Then the determinant of A is given by, so basically you first multiply by A11, which equals to A, and then you eliminate the first row and the first column. Then the remaining matrix should be this part. So you multiply this by the determinant of E, F, H, and I. And then you take minus of A12. So here A12 equals to B. And then you delete the first row and the second column. And then what remains is D, F, G, I. So you subtract B times the determinant of D, F, G, I. And if you keep this procedure, then the last thing should be C times, I guess, D, E, G, H. So here we frequently write the absolute value of A as the determinant of A. So this thing really are like EI minus F times H. We call the summand, this part, as the cofactor of the given matrix A. So the quantity -1 to the I plus j times determinant of A sub ij. This quantity is called as the ij cofactor of the given matrix A. So let's practice the computation with this example. So suppose that A is given by this matrix, then the determinant of A equals to, so you begin with the very first element. So 3 times the determinant of this minor matrix, 0, 1, -3, 7. And you have to subtract 1 times, so now we pick this one. And we have to delete these two things, which gives you 4, 1, 5, and 7. And plus -2. So the remaining matrix should be this part that equals to 4, 0, 5, -3. And if you calculate the determinant, then this gives you 3 times, I guess, 0 minus -3 minus 28 minus 5 minus 2 times -12. And this equals to 9 minus 23 plus 24, that equals to 10. So notice that we expanded along the first row of the given matrix A, but actually we can expand along any other rows or columns. So let's look at the following theorem. So suppose that A is n by n square matrix, then the determinant of A can be computed by expanding any rows or any column. So basically, we can either choose the element in ith row and then multiply cofactors to calculate the determinant of A, or you can choose jth column to calculate the determinant of A as well. So here, cofactor means, so again, this equals to plus minus 1 times the determinant of smaller matrix. So basically, Cij is given by -1 to the I plus j multiplied by determinant of A, but you have to kill ith row and j's column. So if you just collect the signs of cofactors, then this gives you some kind of like the checkboard pattern. So for example, like the 1, 1 entry here. So if you plug in I equals to 1, j equals to 1, so -1 to the I plus j equals to -1 square, which gives you positive. And if j equals to 2, we get negative. And for j is 3, we get positive and negative and so on. And if you go down from the first column, then the second row, well, if I is 2, then I plus j is 3, which gives you negative, and positive, and negative, and so on, and positive, negative, positive, and you can fill in this like in this way. So this pattern really helps you to keep track of all the signs of the cofactors. Okay, so let's pause the video and try to calculate the determinant of the given matrix by using the cofactor expansion. Okay, so let's solve this problem together. So the first thing you want to do is to choose the right rows or columns. I think the easiest one should be the thing has the most zeros. And this is because, so basically if you choose this column, the determinant of A equals to 0 times C13 plus 5 times C23 plus 0 times C33 and 0 times C43. And these zeros really reduce a lot of calculation here. So basically this equals to 5 times C23. And this is the same as, so basically, if you keep track of signs by the checkboard pattern above, then the first one is plus and minus, plus and minus. So 5C23 equals to 5 times negative 1, and determinant of smaller matrix. So basically you kill the third column and the second row, that gives you 1, minus 1, and 2, 9, negative 2, 1, and 10, 1, and 2. Now, because there's no zeros in this minor matrix, so you can either choose whatever rows or columns you want. So let us choose this part. Then this gives you negative 5 times 1 times the determinant of negative 2, 1, 1, 2, minus negative 1 times 9, 1, 10, 2, plus 2 times 9, negative 2, 10, and 1. So this gives you negative 5 times, I guess, negative 4 minus 1, and plus 18 minus 10, plus 2 times 9 minus negative 20. So this gives you negative 5 minus 5 plus 8. So these two adds to 29. So that gives you, I guess, 58. So eventually you get negative 5 times 61. And this equals to negative 305. If A is triangular matrix, then we can easily calculate the determinant of the given matrix. So here the determinant is indeed the product of the diagonal entries. And let us see the reason why. So consider the matrix given by this large matrix. Then probably you want to choose the first column to expand because this one has the most zeros. So the determinant of A equals to 3 times, so we need to kill this column and this row, which gives you 9, 2, 6, 5, 0, 3, 5, and 8, 0, 0, 9, 7, 0, 0, 0, 9. And again, you choose the first column of this matrix. Then this gives you 3 times 9 times the determinant of the smaller matrix, which equals to, that equals to 3, 5, 8, 0, 9, 7, 0, 0, 9. And again, if you run the same process, that gives you 3 times 9 times 3 times the determinant of 9, 7, 0, 9. But we know this equals to 3, 9, 3, and 9, and 9. And if you calculate this, you will get 65, 61. So the point is, the determinant of the triangular matrix is the same as the product of the diagonal entries. Okay, so this matrix is another triangular matrix. So how can you calculate the determinant of A? Well, this is certainly the multiplication of diagonal entries, which gives you 2 times 2 times 8 times 8. That equals to 2 to the, I guess, 1, 2, 3, 4, 5, 6, 7, 8. So 2 to the 8th. And this should equals to 256. So I want to note that the determinant is only defined on a square matrix. So basically, for example, if A is given by, say, 2, 3, -1, 5, 4, and 0, then this is 2 by 3 matrix. So in this case, because A is not a square matrix, the determinant of A does not exist, or it is not defined on non-square matrices.